Good day and welcome to Math 111H Calculus 1 Honors, The Joys of X. Today we'll discuss how we can put together information that we've learned in prior courses as well as in calculus and use that information in order to sketch some curves. Let's see how we do that. Here are the issues to consider when sketching curves. First of all, we want to understand the domain of the function because we don't want to try to sketch it in regions where it doesn't exist. Next, we can look into finding the intercepts of a function. It's easy to plug in x equals 0 to find the y-intercept. Sometimes it's easy to solve for where y equals 0 as well. And that gives us information about where the function is positive and negative, since the function can only turn from positive to negative or negative to positive at points where the function equals 0 or at points where the function doesn't exist. We also look into symmetry if the function is odd or even or periodic, as that can simplify our work. We look into asymptotes. What happens to the function as x gets large? Those are horizontal asymptotes. Are there certain values where the y value goes without bound to plus or minus infinity? Those would be vertical asymptotes. And then there's slant asymptotes, when the numerator of a function has order exactly 1 greater than the denominator. We can also use the first derivative, f prime of x, which gives us the intervals where a function is increasing and decreasing, and we can use that to find local maxima and minima. And we can also use the second derivative, f double prime of x, to find regions of concave up behavior as well as regions where the curve is concave down, and where a curve changes from concave up to concave down, called inflection points. And then we'll sketch the curve. So let's consider an example. We'll consider f of x is x e to the negative x. So here we're going to start with the domain. X can be any real number. We can plug in x, any x value, into x e to the minus x. Next we look into the intercepts. We let x equal 0, and that simply says that y is equal to 0 there. X-intercepts, well, where can y equal 0? Y equals 0 where either x is 0 or e to the minus x is 0. But e to the minus x is never 0, so just where x equals 0, which gives us that same point. X equals 0, y equals 0 is both the x and the y-intercept. Then we could check to the left of x equals 0. We see x is negative, and e to the negative x is always positive. So we have a negative times a positive. So if x is negative, the function is negative. Similarly, if x is positive, the function must be positive. So we know the curve must have some sort of behavior as shown by the green line, that crossing through x equals 0, y equals 0, going from negative to positive as we move to the right. Well, there is no symmetry to discuss in this case. Typically, you'd look into symmetry if all the terms are even, for example, cosines or x to an even power kinds of terms, or if all the terms are odd, we would see if the function is odd, for example, sine or x to the odd powers, or if all the terms are periodic, sines or cosines in some simple way. That doesn't apply for x e to the negative x. Next, we could look into asymptotes. For the horizontal asymptotes, we ask what happens as x gets large. As x goes to infinity, well, what happens? We have x goes to infinity, e to the minus x is going to 0, and then working it out through L'Hopital's rule, we can find that as x gets large, that the y value gets close to 0, but we already knew that the curve was positive, so the y value is getting close to 0 from the positive side as x gets large, as shown on the top here. As x goes to negative infinity, well, then we have negative infinity times e to the plus infinity, which is minus infinity times a plus infinity, which is a negative infinity. So the function would be getting very, very negative as you go to the left. Vertical asymptotes, well, there you deal with x values where y does not exist, for example, where a denominator is 0. And to deal with slant asymptotes, you'd consider when the numerator has power exactly 1 higher than the denominator, and you'd use long division to figure out what is the line that the function gets close to as x goes to infinity or to minus infinity. In terms of the first derivative, how do we use that to sketch our curve? Well, the first derivative of x e to the minus x is, well, the first x times the derivative of the second minus e to the minus x, giving us a minus x e to the minus x, plus the second times the derivative of the first, which gives us an e to the minus x. We simplify, we get 1 minus x times e to the minus x. We set the first derivative equal to 0, so 1 minus x is 0, or e to the negative x is 0, and that tells us that x is equal to 1 is our only point where the derivative is 0. The derivative always exists, and so we can note that to the left of x equal 1, our first derivative is going to be positive times a positive is positive, so the function's increasing to the left of x equal 1. For x is bigger than 1, 1 minus x is negative. E to the minus x is always positive, so we find that the derivative is negative for x bigger than 1, so the function's increasing until you get to x is 1, decreasing from x equal 1 on, and so at x equals 1 you have to have a local maximum, and one can plug into the original function x e to the minus x. If you plug in x equal 1, you find the y value is 1 e to the minus 1. So we have a local maximum at 1 comma 1 over e. For the second derivative, well, we take the second derivative of the function. We find that that's x minus 2 times e to the minus x, which is equal to 0 when x is 2. And we can plot on our number line to the left of x equal 2 that we find the second derivative is negative because the x minus 2 piece will be negative. The e to the minus x, again, will always be positive. If x is bigger than 2, then we find the second derivative is positive. So we have a curve that's concave down to the left and concave up to the right. So at x equal 2, we go from concave down to concave up. And so now we're going to put all these pieces together. We kind of have a feel for what the curve must look like. And here we have it, that the curve is going down to minus infinity as we move to the left, goes through 0, 0, local maximum at 1 comma 1 over e, an inflection point going from concave down to concave up at x equal 2, y equal 2 over e squared, and the curve is going to y equals 0, toward y equals 0 as x goes toward infinity. Okay. Let's just take a moment to review once again that first we deal with the domain of the function. We then look into the intercepts, find where the function is positive and where it's negative. Consider the symmetry, whether the function's odd, even, or periodic, or none of them. Look into the asymptotes. What happens as x gets large? When can y get large? Do you have a slant asymptote? Look into the first derivative for intervals where the function's increasing and decreasing, local maxima and local minima. And then look into the second derivative to find regions where the curve is concave up, concave down, and where there are inflections. Let's take a moment for math culture. A somewhat plump woman walked into a bakery and bought a cherry pie. Would you like it cut into 6 pieces or 8 pieces? The salesperson asked. You better make that 6 pieces, was the reply. I'm on a diet. Thank you for joining us today. Have a great day, and may the power of math be with you.